Hello everyone, this is Anshu MS17098 and I will be presenting my term paper on Transmon Qubits and Josephson Junctions. Transmon Qubits, a flavor of superconducting qubits, utilize the phenomena of superconductivity and quantum electrodynamics. They are one of the most promising candidates in the race to make a fault-tolerant quantum computer and are used by IBM and Google as the building blocks of their model. First, let's start with superconductivity. Superconductors show two very peculiar behavior. The first is the existence of a critical temperature. As one can see from the graph, for a normal metal, the resistivity tends to go to zero at 0 K. However, for superconductors, they abruptly drop to zero at a finite temperature Tc. The other is the Meissner effect, where inside a superconductor, the magnetic field is always zero. Let's talk about the Bardeen-Cooper-Schrieffer or the BCS theory of superconductivity. It is considered a Fermi sea with radius kf, which is the Fermi wave vector and the Fermi energy. We consider two electrons which lie just outside the filled Fermi sea, one with the wave vector plus k and the other with the wave vector minus k. Both of them have the same energy. The two-electron Hamiltonian is given by this, where V is the interaction potential energy and K is the individual kinetic energy, defined by the Fermi energy. We define the interaction potential such that it's attractive and constant for the given region and is zero otherwise. After a few assumptions and calculations, we arrive at the binding energy of the Cooper pair. This energy is lower than the energy of the two unpaired electrons, thus favoring the formation of Cooper pairs. The Cooper pairs are formed from scattering of electrons and phonons. Here's an animation showing the movement of Cooper pairs as they move through a crystal lattice. As we can see from this Feynman diagram, the phonons produce a net interaction between a pair of electrons. The Josephson junctions are formed by placing a thin layer of insulator between two layers of superconducting material. In 1962, Brian Josephson predicted that the superconducting electron pairs could quantum mechanically tunnel through the insulator. He later on won a Nobel Prize for the same. Here are two layers having a quantum phase pi L and pi R. The bias voltage is V and the Josephson current that flows is Ij. Here on the right is a scanning electron microscope image of a real Josephson junction and is scaled at 100 nanometer. Here we find two aluminium wires separated by a thin layer of aluminium oxide. Now, while describing the Josephson tunneling, the superconducting state is considered to be quantum mechanical with the wave function root rho e to the power I theta, where rho is the charge density and theta is the phase factor. By Stokes' theorem, we can relate the quantum phase factor to the magnetic flux. From the quantization of magnetic flux and after applying the Schrodinger's equation, we arrive at these two formula where T is the tunnel coupling, V is the bias voltage, N1, N2, phi1, phi2 are the charge densities and the quantum phase of the superconductors 1 and 2 respectively. Now, these terms can be rewritten to define the Josephson current Ij, V, which is the voltage across the junction, Lj is the Josephson inductance, which comes from the Ohm's law for an inductor. The Josephson energy is defined by this. Now, the Cooper pairs will tunnel back and forth due to the quantum mechanical tunneling, and the frequency of tunneling is defined by this factor Ej. We're interested in what's interesting about the Josephson junction is the non-linearity it produces, which can only be achieved by quantum mechanical description. We will see ahead how this non-linearity plays a crucial role in the realization of Transmon qubits or artificial atoms. Now, first of all, in reality, there are no two-level systems. We just isolate our studies and experimentation to one particular transition, say from state 0 to state 1 of a multi-level system. For instance, let's look at the energy levels of an atom. We know that these levels are anharmonic, that is, the energy difference between every two states is different. To form a qubit, we limit ourselves to the transition from, say, the ground state to the first excited state and consider it a two-level system. We can control the state of these atoms by providing it with an energy corresponding to the energy gap. We shine lasers with light corresponding to the transition frequency of that particular transition to manipulate the system. We can also make artificial atoms to work as qubits, and Transmon Qubit is one such example. We do so to gain the advantage of lesser time to create superpositions and the freedom to customize and improve the design we engineer. Now, here this illustration depicts a Transmon qubit and is scaled to the order of hundreds of microns. We have an dielectric substrate on which we mount two pieces of metal strips connected by an inductor. Though the actual inductor is nonlinear, to understand the effect of nonlinearity, we first assume it to be a linear inductor. We apply an electric field across the metal plates to create a charge separation, which leads to an electric field, which leads to a voltage. Further on, current flows, which gives rise to a magnetic flux. The entire setup can be approximated as a capacitor and an inductor, as shown in this circuit diagram. Now, after applying the Kirchhoff's laws, we arrive at these equations, which highly resemble our mass on a spring motion. To draw an analogy, we can think of the flux as the position, the capacitance as the mass, the charge as the momentum, and inverse of the inductance as the spring constant K. Now, to move to the quantum formalism, we just use the canonical quantization to define the quantum Hamiltonian and other quantum operators like the annihilation operator, the quantum flux operator, and the charge operator. Here, this ZPF refers to the zero-point fluctuation, which is defined by these formulas. Its physical manifestation is in the form of fluctuations or variance found in the charge and flux at the ground state. On solving for the eigenstates and eigenvalues of the Hamiltonian, we get the following result. As expected, the energy intervals are constant and at h bar omega naught. If we provide some energy to the system using a microwave source, nothing prevents the system from performing all the available transitions. So instead of getting a superposition between the 0 and 1 state, we get a superposition of all the available states, which is highly undesirable. Now, we finally introduce the nonlinearity in the form of a Josephson junction. All the other formalism remains the same, except that now we have a cost dependence in the energy of the inductor, which leads to an inharmonicity in the Hamiltonian. On performing lots of calculations and using Taylor expansion and rotating term approximation, we finally reach the solution for the Hamiltonian as shown. As visible in the graph plotted, the energy levels now differ. We can excite the system by, say, omega qubit, and the only transition that occur will be from 0 to 1. We hence limit our system within these two states and treat it as a qubit. The future goals of this paper can be the following. It can actually proceed to some very exciting domains. The first is qubit control, that is, what circuitry goes behind performing logical operations on this Transmon qubit. The other thing I came across was how the noise sources are parameterized in the existing theoretical equations and how it turns into an optimization problem. I also hope to learn Blender so that I can make all the illustrations on my own. Here are the references. Thank you.